Hello everyone, I am Shahab Shadan and I am very glad to have this opportunity to briefly present you the project I have done for the specialization course Advanced Data Science Capstone of the technology company IBM in Coursera platform. As you see, the project has the title Survival Prediction in case of heart failure. So let's begin. We begin with some background. Cardiovascular diseases kill approximately 17.9 million people globally every year, and that is almost 31% of all deaths globally every year. Heart failure happens when the heart cannot pump sufficient blood in the body to meet its needs. Moreover, there are many institutions and foundations who want to increase the survival rate of heart failure. To name one, British Heart Foundation, BHF. These facts were taken from World Health Organization, The Guardian, online news of the United Kingdom, and the National Heart Lung Blood Institute of the United States. Use case. We begin with some things that we already know. We know that we can analyze the body features of the patients. We can analyze the clinical laboratory test values. And we can, out of this analysis, we can identify patterns and correlations. What we also know is that doctors and nurses are pretty quite unable to predict which of the patients who are now at hospitals and who all had heart failure previous couple of days ago, which of those patients would be in danger of death in the next days? Well, they will say probably none of them, because all of them seem to be in a normal situation and everything seems to be normal at the moment for the patient. On the other hand, machine learning can distinguish between relevant and less relevant features. And by features, I mean features extracted from the medical records. Therefore, the machine learning can predict which patient would be most likely in danger of death. And if doctors and nurses use these programs and models, they can take care of the patient who is most likely in danger of death. So, consequently, the patient handling, patient care would be more optimal and correctly prioritized. Moreover, much time would be saved, and most importantly, the survival rate of heart failure will increase. Let's have a look at the data sets which was used in this project. As you see, they are the column titles, they are the features provided. Around 300 patients are in this data set. They are real patients, so this is real data, which makes it a very valuable project. The data we had of age of the patients, whether the patient had anemia, creatinine, phosphokinase, diabetes, ejection fraction, high blood pressure, platelets, serum creatinine, serum sodium, sex of the patient, whether the patient is a smoker, and the follow-up period at the hospital named time. And we had also the information whether the patient has died or not. So this is a supervised classification problem. I cited here also an article which I read. They have worked on this specific data set, so I cited here and they inspired me to do this project. Here we come to the data exploration. To explore data, I used mainly data visualization. And I will show only two examples due to the small amount of time which is specified for this presentation. The first example is a pie chart for the feature smoking. As you see, we can see the distribution of Boolean features like smoking in this case. On the left side, you see 32.1% are smokers in this dataset, so almost a third, and 2/3 are non-smokers. On the right side, we see the distribution of smoking and the death events simultaneously. The light blue, 10%, are the dead smokers, and the dark blue, 22.1%, are the survived smokers. So, like a bit less than half of the smokers have died. Here, the pink color is for the dead non-smokers, 22.1%, and the survived non-smokers, 45.8%. So also here, a bit less than half of the non-smokers have died. So we can say till now that there is no considerable correlation between smoking and death event. The next example here is for the future age. We see the distribution of age and death events simultaneously in this marginal histogram. We see the red box plot, which stands for the dead patients, and here the green box plot for the survived patients. So we see the distribution of the death here, and we see how the age is distributed among from 40 to 95. And if you look at the data here, the median is 65 by the dead ones. This means 50% of the dead patients were older than 65. And as you see here, the third quartile of the survived patient is also 65, meaning that 75% of the survived patients were younger than 65. So we see here a tendency that the dead patients were considerably older, and we can say there is a correlation between death event and age. The architectural decisions I made throughout the project, this is all a loop, and I went back and forth, and this is the final decision I made. Of course, data cleansing, I searched for missing and invalid values. There were none. Luckily, a very clean data set, perfect. I used 75% of the data set as training set, and I used it for the learning process, and the rest, 25% for the as the test data set, which was not used for the learning process and used for the final model performance evaluation. The data has been scaled using standard scaler. Cross-validation method was used with 5 splits, so validation sets are automatically created within the grid search. I use feature selections, of course, but I use multiple feature selection methods. One was the correlation matrix. I use 3 correlation methods: Spearman, Kendall, and Pearson, and I took one feature set on which all 3 correlation methods agreed on. So this is one feature set. And I used also the feature importance calculation of some specific algorithms, which I will explain later. And so I took other feature sets also, and I trained models on them. I use one deep learning algorithm, artificial neural network, and 2 classical machine learning algorithms, namely random forest and logistic regression. And last but not least, recall was chosen as the main metric for model performance evaluation. But why recall? Well, recall is a very good measure when the cost of false negative is too high. But what is false negative in our case? In our case, false negative happens when patients in danger of death are labeled as surviving. So this means that the patients who are actually going to die don't get the necessary care, and they die as a consequence. And this is exactly the thing which we want to avoid. But false positive, on the other hand, happens when patients who are actually going to survive are labeled as dying or in danger of death, and they get extra care. And well, that's not a bad thing, but that's a big waste of time of doctors and nurses, because actually the patient didn't need that. This time and effort of doctors and nurses could be put on patients who were really in danger of death. So the main goal is to reduce false negative, and recall is good for that. Another reason for recall is that dataset is imbalanced. Almost 68% of the patients have survived in this dataset. So this means if you use, for example, accuracy as the main metric, it would be not precise enough. Why? For example, let's say your model predicts always that the patient survives. and you will get 68% accuracy, and that doesn't make any sense. So, like, by imbalanced data sets, it's better to have a recall or precision or F1 score metric. And I chose recall because false negatives are very critical here and they should be avoided. So, artificial neural network, two best models I took from them, one trained on all 12 features and one on their correlation methods, feature sets, age, ejection fraction, serum creatinine, and time. Those were the features selected by the correlation matrices. And random forest classifier, as I told you, I used all the 12 features or and and the features selected by the correlation methods. And also I use the feature importance calculation of random forest algorithm, which is based on impute decrease. And I got multiple different feature sets. So I chose two of those feature sets, two different feature sets, and and I did it by removing the least important features. I did the same thing for logistic regression, but based on the coefficients and of course the feature sets of correlation methods and also all the features. So I got three best models out of this. And here are the results. The best artificial neural network model had a recall of 70%. The best of the random forest algorithm had a recall of 90%. Excellent result. And the best of logistic regression had a recall of 70%, whereby all had 70%, but so I had to move on to the second priority in the metrics, which was the precision 78%. Here I put all the three best models all together from the three algorithms, and as you see, the random forest algorithm 90% recall has the best result, and this was the model which used the features selected by its own feature importance calculation. And as you see here are the features: creatinine, phosphokinase, ejection fraction, platelets, serum creatinine, serum sodium, and time. And with a recall of 90%, we had the excellent result, an accuracy of 91%, and I saved this model as the last and best model for this project. Thank you for your time and thank you for your attention.